This should not be section 3.4. This should be section 3.5. So I'm sorry about that. If you guys could go ahead and change that typo. Okay, today we're going to continue factoring down polynomials, but we're going to take a look at how you could maybe be given the factors and develop the polynomial, and also how sometimes those zero values could be imaginary or irrational. So obviously those terms, we just want to revisit them to make sure we know what we're looking at. How do you know if a number, first of all, is rational? Does anybody remember? Yes, it's a ratio of two integers, which, I like the way Jaden said it, can be put into the form of a fraction. So the technical definition is ratio of two integers, but I like the way he said it, just a fraction. The number 1/2 is rational. The number 2 is rational because it could be looked at as 2 over 1. The number 5 is rational. Okay, yesterday we looked at finding a lot of rational zeros. You can see it on the board with all the possible rational zeros that the rational zero theorem brings. Well, today we're going to look at how might a function have irrational answers as well, and also look at imaginary. So let's just quickly remind ourselves of that vocabulary. What does it mean to be irrational? Awesome. Pi is an example, and exactly what Catherine said, a number that cannot be written as a fraction. If you looked at the decimals, it would be decimals that either don't end or don't repeat. But we could use that. It just cannot be written as a fraction. And then Linda even went on to give us some examples. There's a pi. Square root of 2 would be a good irrational number. You can't put that in a fraction. And if you looked at its decimal equivalent, it would not end and not repeat. Example like square root of 3. And then lastly, we're going to have some vocabulary in this lesson that involves a complex number. Complex number comes in the form of a number, oops, sorry, that should say A plus some imaginary with it. Now, every single number is defined as complex, and I'm going to show you kind of two numbers how you could see these as complex. Example, if you have the number 2, the reason that that is complex is because it can be written in the format of 2 plus 0i. Or if you have a number like 1 plus I, that's another example of a complex number. It just contains an imaginary component with it. Okay, that's some of the main vocabulary that will help us solve these theorems and then simplify within, or understand the theorems and simplify within. This first theorem that we look at, it's called the fundamental theorem of algebra. And it states that every polynomial, and they gave just kind of a generic form, with complex coefficients has at least one complex zero. At least one complex zero. And remember, when you're looking at the word complex, that just involves all numbers. It involves 2, it involves 1 plus I. So basically this theorem states that every single polynomial will have at least one zero value. Now the next theorem I actually think is more helpful. It's called the zeros theorem. And the zeros theorem states that every polynomial of a degree where n is greater than or equal to 1 has exactly that amount of zeros, provided that a zero of multiplicity k is counted k times, meaning it could have multiple zeros. So let me kind of bring that home with an example. Example, if you have something y is equal to x squared minus 4, according to this zeros theorem, then how many zeros should this function have? 2. Because you have a squared, the highest degree is 2. Therefore, according to this theorem, we should have 2 zero values, provided one could be a multiple zero. So it could occur twice when you factor it down. So I'll just say provided, could be, could have multiple zeros. Now these theorems are so helpful because they give us insight into how many zero values we should find, whether rational, irrational, or complex. The amount of zeros will need to match the degree of the function. So let's go ahead and let's just use what we looked at yesterday and try the following example. So use the processes from your homework last night, try the following, and this is supposed to say find all zeros. Or find, actually, you know what, not zeros, let's call those solutions. Sorry, find all solutions. Okay, so given that 1/2 is a zero, let's remind ourselves what we did in last night's homework. What would we do first to find the others? Well, first of all, how many solutions should we find? 3. Good, because it's a degree of 3. So how am I going to find the other 2? What do we do, Jeremiah? Yeah, do synthetic division, right? So take the fact that we have a 0. So we have x equals 1/2. We'll put that in our box. Line up our coefficients of 4, 6, -2, -1. Bring down the 4. Half of 4 is 2. Add straight down. 6 plus 2 is 8. Half of 8 is 4. Add straight down. -2 plus 4 is 2. Half of 2 is 1. Add straight down, and that comes out to be 0. So far, this function factored would look like x minus 1/2 times 4x squared plus 8x plus 2. So that's what I have so far. And then how could so right now I have a 0 value of x equals 1/2. What could I do to find the solutions to this polynomial? We can take out the 2, so I take out the 2, and I would have 2x squared plus 4x plus 1. And then I could try to factor this guy, but is it factorable? Not factorable, so that's not going to work. So what can I do instead to find the other values? Quadratic formula. So I'm going to take this guy up here, use the quadratic formula, and that would give me x is equal to the opposite of b, so -4 plus or minus square root of b squared. What's b squared? 16, good. Minus 4 times a, which is 2, times c, which is 1, all over 2 times the value of a, which is 2. So that would bring me -4 plus or minus square root of 16 minus 8, which would give me 8, all over 4. Can that be simplified? Yep. What can the square root of 8 be rewritten as? Good, 2 root 2. And then what can I do? Divide out a 2. So I could divide out that 2 from the numerator, which would leave me with -2 plus or minus root 2. This is over 4. But now I can see a factor of 2 that can be reduced. And then, do you guys remember that when we dealt with these types of numbers, we wrote them as -1, or we often wrote them as -1 plus or minus 1/2 root 2? Does that look familiar? Yeah, because we just took this number divided it by 2 and this number divided it by 2. So really, how many more solutions do we have? Two others. So we have 3. You're right. We have x equals 1/2, which is a rational 0. This we could have found from the rational 0 theorem that you guys used in yesterday's homework. And these 2, what types of numbers are these 2? Irrational. And you could look at it as -1 plus 1/2 root 2 and -1 minus 1/2 root 2. Another vocabulary word that's going to come in this lesson that we have to remember what it means is a conjugate. Do you guys remember what conjugates are? Anybody remember conjugate? It's weird. They're opposites. These two right here, these are actually conjugates of each other. Conjugate, as a quick reminder, it just means if you have an A plus B, its conjugate pair is A minus B. So A plus B conjugate pair is A minus B. Which one? Because the -2 was negative? Because it was the opposite of B. So my B value, looking back at this quadratic, was 4. So when I used the quadratic formula, it became -4, and then I just maintained it with me as I simplified. Good question. Okay, now that I revisited that terminology, conjugate pair, let's see if we can answer this question. So actually, I'm going to pause this. I want you to see if you can, with your partner, explain why irrational zeros, so for example, those are irrational zeros, come in conjugate pairs. So with your partner, just discuss for like a minute why you think that would be, and then we'll come back. All right, so Vince is saying, I like the way he said it. He said the reason you have a conjugate pair is because it really comes right before the radical. It's the plus or minus in the quadratic formula. Or if you're solving an equation and you're taking a square root, you need to take into account the plus or minus. So what this means is if you have an irrational answer to a polynomial or a irrational solution, it's going to have a conjugate pair. And that's because it's because of the plus or minus in the quadratic formula. In the quadratic formula. Now, I just have a question for you. What if this was the square root of -2? How would that change your answer? It would be imaginary. It would still be a solution to the polynomial, but it would be not a real solution. It would be an imaginary solution, which is still considered under the realm of complex numbers. So what that implies is if you are now given imaginary zeros, they are also going to come in conjugate pairs. So let's use that understanding to try the following. It says find all the zeros, meaning all real and irrational and imaginary, of this polynomial given that 1 minus I is a 0. Okay, so it's kind of giving you one hint. If 1 minus I is a 0, what else do we know is a 0? 1 plus I. Okay, so that would be like step 1, find the conjugate. So 1 minus I is a 0. Therefore, 1 plus I is a 0. That's step 1, find the conjugates. So this would be like your step 1. How do you think I could, well, first of all, how many zeros really should I have? 4. One of them could occur twice, but I should have 4 zeros. So if I have 2 of them, if I have a 1 minus I as a 0 and a 1 plus I as a 0, any ideas of what I could do maybe to find the other 2? What did you say, Jaden? So, well, we could do synthetic division, but synthetic only works with rational numbers. But that would be a good place to start if I was given rational numbers as zeros. Long division. That's good, but if I do long division, then I would want to multiply these 2 out, their factors, to see, well, what do I have left after I divide this by 1 minus I and 1 plus I? So, quick reminder, if 1 minus I is a 0, then you know that x minus 1 minus I is a factor. And if 1 plus I is a 0, then I know x minus 1 plus I is a factor. Just like if you had 2 was a 0, you would know x minus 2 is a factor. So step 1 is to find your conjugates. I'll just go ahead and list this out because I feel like after we go home after a long day, I'd be like, what did we do? So step 1 is to find the conjugates. Step 2 is to multiply the factors. Multiply the factors. And then we are actually going to use what Lydia said. We're going to then do long division. This is good stuff. Okay, so when I have this multiplied out, when I multiply this in, I'm going to distribute that negative. So that would give me x minus 1 plus I times really x minus 1 minus I. Do you guys remember how to multiply a trinomial by a trinomial? It's a bunch of distributing, just like FOIL. So I have to distribute this x into all 3 terms of the second trinomial. So x times x gives me x squared. X times negative 1 is a negative x. X times negative I would be a negative xi. What would I distribute next? The negative 1. So I'm going to distribute the negative 1 to the x. I'll get negative x. Negative 1 times negative 1 is positive 1. Negative 1 times negative I would create a positive I. And then lastly, I need to distribute what? The I. So I times x would give me xi. I times negative 1 gives me negative I. I times negative I gives me negative I squared, which is something. Negative I squared. I remember that from last semester final. What is it? It becomes positive 1, right? Because what is I squared equivalent to? Negative 1. I squared is negative 1. So the opposite of I squared is equal to positive 1. You guys have really good memories. Okay, so now let's combine these like terms. So if I combine these like terms, I will have an x squared. Negative x and negative x would create a negative 2x. What happens with negative xi and positive xi? They cancel. What about 1 and positive 1? 2. And then the I and the negative I cancels, right? So right now, I have that if you took this big polynomial and divided it by its zero values, if you took its 0 values and multiplied them out, we have one of the factors. Now, Lydia said then use long division. So now what should we do using long division? So I have this, which is where these two came from. If I factored this down, I would get back up here. So my step 2 is to multiply the factors. Step 3 would be use long division. And actually, I'm just going to do it with you guys, and then I think it'll make more clarity after we have the answer. So we're going to divide that big polynomial, x to the 4th, minus 7x cubed, plus 18x squared, minus 22x, plus 12. And we're dividing that by what we found. X squared minus 2x plus 2. Go ahead and complete this with your partner, and then we'll check our answer. So go ahead and do that long division problem.
I told her during passing period. I told her during the call.
All right, guys, let's check our work. Did you check this with me? I feel like my mind's a little cloggy. Did we have x squared minus 5x plus 6? I think I said cloggy. Okay, good. So what this means is that this times this, x squared minus 5x plus 6, that's what our polynomial factored down into. So that's what this big guy factors down into. Now, we were given 1, 0. So technically, if you factored this puppy back down, you would get those two zeros. X equals 1 plus I and 1 minus I. How do you think I can find the other two zeros from what I did with long division? Just factor it down. So if I factor this guy back down, then I'll have x. Let's see, the last term's positive, so I'm going to have the same sign as the middle terms. So it'd be 2 and 3. So what are my other two 0 values? 2 and 3. Did we find 4 of them? Yes. Happy days. All right. Do we feel like we're in like college algebra at this point? Like multiplying, distributing, all this crazy stuff? Jeremiah?
Will we be asked to graph imaginary?
No. You would not be asked to graph this. Yes.
Oh, geez.
Good stuff. And you have to graph on a complex plane. It's fun. It's fun.
Is it like?
Yeah.
Actually, I don't want to.
All right, guys, let's keep going here. We're going to keep continuing to consider these types of zero values. Look at the two equations. I'd like you to ask, are the zeros for an equation unique? In other words, can you have more than one equation with the same zeros? Let's see. Yeah, you guys are already shaking your head yes. So let's see how in the example 1 and example 2. What would I do in example 1 to find the zero values? Just take out the 4. I'd have x squared plus x minus 6. And then what would I do? Just factor. Oh, this was the nice algebra. Plus 3 minus 2. And then what were my zero values then? 2 and negative 3. Now, if I found the zero values for example 2, I would get the same thing, right? X minus 2, x plus 3 would factor down into those pieces, so my answers would be x equals 2 and x equals negative 3. Were the functions the same? No, if I graph them, in fact, they would look, specifically their minimum or their maximum would look different. So what that means is when you're working backwards, which is what we've been doing, when you're given the zero values and you are determining the actual function, there may be a constant that you have to consider. So I'm going to show you that just as we do the next few examples, and that will hopefully bring clarity of why it could be this answer or this answer. So let's go ahead and let's try do it all, but we're going to do it all backwards. Write the equation of a polynomial with the given zeros, given that the zero is at x equals 1, x equals negative 1, and x equals 0. You're going to find a degree 3 polynomial with these zeros. So how do you think we would work backwards? If I have all the zero values, how can I go back and find the original function? Yep, this came from, if this came from x minus 1, yep, this one would come from x plus 1, and this one would come just from an x. If you are unclear of how to get back to the factors, you're just basically setting these equal to 0. So you would get x minus 1 equals 0, x plus 1 equals 0, and x equals 0. That's where they came from. And now I'm going to go ahead and I'm going to take this and I'm going to just multiply it out. So what would I do with the first two pieces? FOIL. So that would give me, do you guys remember the shortcut? Let's get some shortcuts in here with all this algebra. Do you remember a minus b times a plus b? Yeah, it becomes a squared minus b squared. So what would x minus 1 times x plus 1 become? X squared minus 1. Just those nice shortcuts. Times x. What would I do with the x? Distribute that in. So that would leave me with x cubed minus x. This would be my function. However, it might not be just that. It could also be a constant times x cubed minus x. So just as you're taking this into consideration, it might be just a basic function, but you could have had a constant that had been multiplied through. So when you see the answers in tomorrow's answer key on the surface here, I would ask you to write it in both ways. And this is because when you get to pre-calculus, you will always have to actually find what is that constant value based off of the solutions that you'll see on the graph. So right now, just to make sure that you guys will jump up in that level, just make sure you recognize it could look like this and it could look like this. All right, let's do this last one together, and then I'll have you try the last one with your partner. Find a polynomial of degree 3 that has zeros at 2 and 1 plus root 5. quick question for you. What type of number is 2? Is it rational or irrational? Rational. What type of this number is this one? 1 plus root 5. It's irrational. All irrational numbers will have another solution paired with it. It will have the conjugate pair. And that comes from where it came from in the quadratic formula. So if I know 1 plus root 5 is a solution, what else do I know is a solution? Good, good. 1 minus root 5. So I really know all 3 of my zeros. I know 2, I know 1 plus root 5, and I know 1 minus root 5. So when I put these back into factored form, I'm going to put it back in as x minus 2, x minus that 0 value, 1 plus root 5. Is it important that I put that in parentheses? Yeah, because what am I going to have to do with that negative? Distribute. Good. And then x minus the quantity 1 minus root 5. And we can go ahead and multiply that out. Are these, can I use that trick, a minus b, a plus b equals a squared minus b squared? You could. So if I was doing that out, my a value would match up with x. My b value would match up with 1. Oh, actually, I can't here because b is not the same. Ah, shucks. I was hoping I could do a shortcut there, but I can't. So let's go ahead and let's multiply this out. What do you guys want to multiply first? The last two? Sounds good. So first times first would give me x squared. Outside would give me a negative. Actually, is it okay if we apply the negative in first? Let's apply the negative in first so we don't get lost. So this would actually become x minus 1 minus root 5. And then x minus 1 plus root 5. And I have that x minus 2. Why don't you go ahead and multiply this out with your partner, and then we'll check the answer at the screen.
Still in that first section. Right. So we got the negative 1 times x, then negative 1 times negative 1. Well, that's almost. Positive root 5 will be negative root 5. Negative 5 multiply over to the x. Negative x root 5. Positive 5. And then negative 5 times positive 5 yay. Okay. Yeah. Here's what I've done so far. X times x. X times y times power 6. And then x times. I still have positive 5.
Okay, guys, just as a suggestion, I would multiply the last two out first because there tends to be a lot of pieces that cancel when you multiply the factors from the conjugate pieces. So once I did that, then I distributed the x minus 2, and I got x cubed minus 4x squared plus 8. The last one's actually much easier. It says find a polynomial of degree 3 whose zeros are at 6 and 3i. If we have zeros at 6 and 3i, what other zero do I know has to exist? Negative 3i. Because the conjugate of 3i would be negative 3i. If you could look at it as 0 plus 3i, so the conjugate would be 0 minus 3i. Okay, so if I put this back into factored form, it would be x minus 6, x minus 3i, x plus 3i. Now this does match the pattern a minus b, a plus b. So if you multiplied these two behind first, you would get x squared minus b squared, so minus 3i squared. Oops. I still have that x minus 6 out front. Oh, that becomes x squared minus 9i squared, which is actually x squared plus 9. So if you had multiplied that all out, you would get x cubed minus 6x squared plus 9x minus 54. Sorry, guys. Wah! All right, so your homework is on Academy Central. I think it's 4 or 5 problems. It is I thought so. Let's make sure I have published.
Because I didn't see any homework tonight. I was like,
Oh no, this is upsetting. Thank you, guys. Let me see if I. Thank you for staying with me. It's a good lesson. Oh, man. Oh, I'm still recording.